Welcome to session 2, which is grade 10 physics 2. We're still on wave, sound and light. Remember last time we had a look at the pulses this way, and we did a few terms, right? The best way with these is basically just to summarize them and learn what the actual terms are, what they mean, okay? Now, let's just finish off. We were talking about frequency, right? Frequency and C like that, and we said it's measured in hertz. You've got megahertz, kilohertz, okay? Mega, okay? Kilo 10 to the 3, mega 10 to the 6, okay? Now, frequency it's the same as in maths, right? The frequency is how many times something happens, right? So it's got a frequency of 5 per day. 5 times per day, right? That's a frequency. Frequency in this case is going to be 1 over seconds, which is waves per second. Okay. Now, the last bit, we've now got frequency, right? Waves per second. Remember, we also had the wavelength. Okay, was lambda, and we generally measure this in meters. Okay, we're going to get to a few numbers here in a few secs about the wavelengths that we're going to be dealing with, typical ones, but let's just say it is measured in meters. So what is the speed of a wave then? I'm also going to introduce velocity here. Okay, velocity of a wave. The speed of a wave, well, velocity, speed, remember way back in maths, is measured in meters per second, kilometers per hour. It is basically distance traveled over the time you took, isn't it? It's the distance over the time that we took to do it. So that's that. Now let's look at waves, because we see them moving, and we actually see some days those waves are coming at us very quickly. Some days they're sort of languid and they're sort of gently passing us by very slowly, right? So waves have got a speed, they've got a velocity associated with them. Well, do we have a distance? Well, let's have a look. V, distance, yes we do. Wavelength, hold on. We've got here, the wavelength is lambda, isn't it? All right. But now we need to divide by time, all right? There's our frequency. This is known as the general wave equation. Okay? Let's have a look at the measurements here, all right? What have we got? Wavelength is measured in meters. Frequency is hertz, is 1 over second. And look what we've got. We've got meters per second. So the wave equation is giving us the velocity, the speed of a wave, meters per second. Okay, just before we move on to the longitudinal waves and their calculations, which are incidentally exactly the same, all right? I just want to talk about this. Wavelengths now that we're going to be talking about. Let's look at some wave lengths, right? We've got meters. We've got millimeters. So meter is 1. This is 10 to the minus 3, isn't it? Because we divided by 1,000 to get there. So a millimeter is 10 to the minus 3 meters. Okay. The next level down, okay, is going to be micro, which is times 10 to the minus 6 meters. The next one is nanometer, which is 10 to the minus 9 meters, right? These you do need to write down and remember. But there's a little key to it, is nano 9. Just remember nano minus 9. These are all very short wavelengths. So the distance between there and there is only 10 to the minus 9 meters. which is pretty short, right? It's almost at atomic level, okay? Atomic size of an atom. So what do? We say these are -9 meters, right? Very, very short indeed. So micro, nano. These, for example, are when we're measuring different kinds of waves. We're going to be using those. Okay, that's just was an aside, but something that you need to know. Okay, a longitudinal wave, right? Let's just, for the sake of finishing it off, a longitudinal wave had a compression, rarefaction, compression, rarefaction. Okay, and remember we said that those are our red is wavelength here, right? Exactly the same as a transverse wave. We use the same equation, the general wave equation. Velocity is equal to frequency times wavelength. Okay? Now, the amplitude, particle movement, we've discussed that. It's a displacement. Well, hold on. Here's another word, pitch. Okay? What is the pitch of a wave? All right? We all know that different voices have got different pitches. You can be very low or be very high. Right? Okay, that was a terrible thing of it. But you know, the female voice is higher than the male voice. So you've got a high pitch and a low pitch. Okay? Well, what does it mean? It actually means the frequency. All right? Right? High is a female voice, even higher is a whistle. All right? And the low frequency, okay, is a male voice, right? That'll be the low frequency. Dog growl would be low. You know, that sort of low growl of a dog. Right. That's the pitch, all right? Now, let's have a look. What does it mean? It means, let's just look at two waves here. And, okay, can you see here is my lambda 1, okay? And here is my lambda 2. Lambda 2 is shorter than lambda 1, isn't it? This is a short wave, all right? This is a long wave, right? Now, let's just use this wave equation here. V is equal to lambda times frequency. V is equal to lambda times frequency. This is lambda 1, this is lambda 2. All right? Now, the velocity, this is a sound wave, let's say. The velocity of sound in air, okay, is equal to about 330 to 340 meters per second, which means it's pretty much constant. Therefore, 340 is equal to lambda 1 times f, and v, well, sorry, it's 340, come here eraser, 340 is equal to lambda 2 times frequency, right? This is frequency of the 1, this is frequency of the 2. Right? Lambda 1 is bigger. So therefore F1, okay, is going to be less than frequency 2. All right? It's a lower frequency, the male voice and the female voice. Right? Just using the wave equation, you can see that. All right? Right? So if the frequency is high, the wavelength is short. High frequency, high F, lambda, short. They are opposite to each other. Low frequency, lambda, is longer. Okay? Low and longer. There you go. Low and longer. There it is. Okay? And you just remember low and longer, therefore high must be shorter. Okay? Right. Now, let's have a look. Oops, sorry. I don't want to do that. I want to just I'd moved a bit too far ahead there. All right, now we need to have a look at, there's one last thing here, all right? Let's look in air, all right? The female voice, a female voice has got a frequency of between 165 hertz and 255 hertz. The male voice is between 80 and 180. So let's take the average, okay? Let's take the average frequency here of a female voice. It comes to 210 hertz. You just add those and divide by 2, okay? What is the average frequency there? Add them and divide by 2. I get 130 hertz, okay? So that's the frequency of a female voice and a male voice. Let's now do a calculation, shall we? All right? And take the speed of sound in air as 340 meters per second. All right? Therefore, for the female, velocity is equal to frequency times wavelength. Velocity is 340 because the velocity is the same for the man and the woman. The sound wave travels through the air. By the way, it's a longitudinal wave, okay? I've drawn it like that, but it's actually a longitudinal wave that does that, okay? It's equal to frequency, which is 210 times lambda. Therefore, lambda is 340 over 210, and that comes to 1.62 meters. All right? Let's look at the male voice. Okay? Velocity is equal to frequency times lambda again. 340 is equal to, now we've got 130 times lambda. Therefore, lambda is 340 over 130, which is going to be equal to 2.62 meters. Okay? So you can see it's longer, shorter. Okay? Right. Now, let's have a look at the loudness. You see, these are all terms that we've just got to go through before we can start getting involved. Same as chemistry. We're going to go through a lot of words, developing a vocabulary. What do we mean by this? What do we mean by that? So what is loudness? Loudness. How loud? How loud? The difference between a whisper and a shout. A shout is loud and a whisper is soft. All right? Loudness, how loud something is measured in something called decibels. Okay? Decibels, and it's abbreviated dB, like that. All right? So now, just to get a feeling for it, speech. Normal speech, like probably what I'm doing now, is going to be, I always do that, 65 decibels. Okay? Loud music can go up to 85 decibels. Okay? All right? We're just getting a feel. A Boeing, a 747, let's just call it aircraft, because it could be an A380, a 747, who knows. But an aircraft is round about 140 decibels. Okay? This will damage the ears, the hearing, permanent. 85 decibels is what's called the threshold. At this point here, 85 and above, we start to damage the hearing of a human being. All right? Now, for example, let's just look at something. What is this? You've heard of this thing, went past the sound barrier. Okay? Pretty cool, okay? Makes a huge bang, right? What actually is happening over here? Well, what is happening here is quite simple. What we're doing is that we are pushing the velocity, okay, of the aeroplane increases, right? It is pushing the sound waves ahead of it. So it is compressing the sound waves, okay? You can go onto the internet and have a look. There's such a cool pic of, I don't know if it's an F-16 or an F-14, one of those US fighter jets going through the sound barrier. And you can see this donut-shaped sort of puffs as it's going through the sound barrier. What is happening is it is exceeding the speed of sound. It is pushing the sound waves right up to that point. It's actually compressing them in front of it like an elastic band. Stretch, 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 until the aircraft is moving faster. Then that energy that it's pushed there just gets released. And you get what is called the sonic boom. Okay? The sonic boom. Essentially, all that is it's a shock wave. It's a shock, oops, that's my spelling. Shock wave, all right, is the sonic boom. It is the energy release. Energy is released. That energy goes, and it goes as a shock wave. A bomb. There was a brilliant scene in Iron Man, I think the first one, right, where his missiles went off behind, and you saw the explosion, and the next thing, everybody got blasted by the shock wave coming forward. Same thing. That's the shock wave, the sonic boom, all right? As an aircraft travels faster than the speed, it is in essence a pressure wave. It is a pressure wave, okay? So, now remember, this time we're just talking about these things, okay? Now let's have a look at for example, velocity in medium. I actually think it's media, okay? Media. That always happens to me, doesn't it? Velocity in different media. What is the velocity in air of sound? Well, we said it was 340 meters per second. Water is 1450 meters per second. Stone is 5,400 meters per second. Hang on, steel is 6,000 meters per second. What does it mean? It means the velocity of a sound wave in air is 340 meters per second. It's almost a kilometer. Let's just do a quick calc just for the thingy. This is almost 1 kilometer, isn't it? Okay, every 3 seconds. 1 kilometer per 3 seconds. If I multiply, that's virtually a kilometer, right? That is why, if you know the old story, if you see the lightning and you start counting, right? The lightning is the light wave, then you hit by the shock wave, right? The thunder it's a shock wave, it's a pressure wave. So if you count the time between the flash, okay, not the TV program, the flash, okay, and the bang is when the pressure wave hits us. You count the time, okay? Let us say you get 9 seconds. Divide that by 3. That tells us that the lightning is 3 kilometers away, which means you'd better be inside and out of the way, okay? Because that is close. That is very close. If you're misfortunate enough and the flash and the bang are one thing, pretty much you just got hit. Or else you probably didn't get hit, it'll change your hairstyle. What actually happens is that the building that you are in probably got hit, or a tree very nearby, because we can't tell that the split second difference between the two. But yes, you take the time between the flash and the bang and divide it by 3. That tells us roughly how far away the storm or the lightning actually is from us. All right? So, and in steel, so if you've got a long steel cable and you hit this end, the sound wave travels at 6,000 meters, 6 kilometers, okay, in a second. That is pretty fast, right? Have you noticed something? That the density, the sound wave, increases with the density. Oddly enough, sound is faster in water, okay? The last part, I think this is the last part of this. All right, yes, is this concept here we have to deal with. Ultrasound, okay? What is ultrasound? The human ear can hear from 20 hertz, which is a whisper, right up to 20,000 hertz, okay? Which is 20 kilohertz. Very low, very high, okay? Okay, now, what are we saying, okay? Now, above this frequency here, humans, we cannot hear it, but animals can. Those whistles you buy for an animal, for a dog, or for a cat, if you can get a cat to come with a whistle. Oddly enough, we seem to have trained our guys to do it, but you will notice people think that it's not real. It's very real, because ultrasound, they definitely can hear it, right? Bats operate in the ultrasound region. So an animal's hearing sounds above us, above ours, because after all, they have developed or evolved to live in the wild where frequencies are different to ours. We don't need it, okay? So we've got that. Now, here's another word that comes in is echolocation. All right? What does it mean? It means, how does a bat find its way around, okay? You've heard the thing, blind as a bat. How does a bat find its way around? It uses echolocation. It looks something like this. Let me just see if I can draw it. You'll find I'm not an artist. I don't even pretend to. I still draw stick men, okay? So let's have a look here and say, right, here's my bat, okay? Here's my bat over here, okay? And he's flying this way, and his wings are there, right? Okay, what does he do? He sends out a little beep signal, okay? A little squeak, actually. A little squeak signal, right? That goes out. If there's a moth over here, that thing hits the moth and bounces back. So the bat now says, aha, he can work out where it came from. It bounced back from there to him. He turns and he knows how far away it is, right? Obviously the moth is moving as well. The bat hones in on the moth, right? And if you've seen some of these on National Geographic, they are amazing creatures, how they can hunt in the darkness. And when they come out of their caves, not at total darkness, okay? I mean, they do come out at sunset. And they're amazing, the way they can hunt and things like that at night. I don't know if a bat actually has vision. I would imagine it has limited vision, but this is how they do it. Echolocation. They send out sound waves and it comes back. That's the same as a dolphin does the same. Okay? It's the same as sonar. You've heard in the movies, you know, in the submarines and things, they switch on the sonar and they ping. Okay? What does that mean? The ping they send out is a echolocation. They send out a ping and that goes out and comes back. And on their radar, they can see, okay, in total blindness, I guess, because there's no eyes looking forward. It's purely relying on the echolocation. The echo, the bounce back, location, place. So you work out where the bounce back occurred. Okay? So, yep, you can see the icebergs, you can see whatever ahead of you. Yeah, a lot of trust involved in that if you think about it. So what is ultrasound used for? Well, we all have heard of ultrasound. When you go, you very often in medicine, right? Okay. You've got, look what I just wrote there. Medicine. Crikey. Right? What do we do in medicine? We use ultrasound because ultrasound is, first of all, it's not as dangerous as X-rays are, right? X-rays, you can only have so many X-rays per year, okay? Even the dental X-rays. So you're limited to the number of exposures to that radiation. An X-ray is a radiation, short wavelength, but highly dangerous, right? The next thing is that there's a less invasive, is an ultrasound. The ultrasound uses sound waves to penetrate and then it bounces back. Usually it's used to view the fetus, okay, in the womb. So what they will do is they've got this, they put on the skin, they put a jelly normally, and then they run over the area with the ultrasound. And what it's doing is it's sending the things down over here. They don't hold it in one spot, they move it around. Why are they moving it? Because as they're moving it, remember the bat was listening there, and these waves are coming back all the time. This is picking up different bounce back times. So as it there, and it bounced back, and there. So it's telling me this is close, that's far. So it can build up a three-dimensional picture of what is actually happening inside there. You get a three-dimensional picture of the fetus, okay, an image, and they use an algorithm, a program that will build up. Essentially, it's building up topography, like a terrain. It's showing us here's a high point, low point. That's what it's doing. Also, it travels through bone and through sinew and through different densities at different rates. So you're building up pictures all the time, right? When they're going to do it, they'll set the machine, and they can set it for its accuracy. They'll set it to show the picture that they're looking for. Okay, that is ultrasound that is used in medicine purposes. Okay, it's used to measure blood flow, and it's used to measure the thickness of the vein walls and various other bits and pieces. You've just got to know that it's used in medicinal purposes. Okay. The next session we're going to talk about is the electromagnetic spectrum. We're actually going to start talking about light now, okay? We're going to talk about photons, we're going to talk about energies of light and things like that, okay? I'll see you in session 3. Sorry, once again, these are a little bit longer. They usually are because it's the intro sections. So bear with me. But once again, also please, I know that in grade 10, there's so much of it that's the learning work, and defining terms. But this is the point where we're actually starting to lay down all, so that when we're talking in grade 11, 12, if you go to varsity, and if I still see you at varsity, some students I still do see them even after grade 12, we talk in the language now of physics, we talk in the language of chemistry, and we talk in the language of mathematics. So everything means the same. If I say to somebody, it is they know exactly what I'm talking about. We are defining the terms. You'll be doing this in life sciences. You'll be doing this in accountancy as well. A balance sheet is, a debtor is, a creditor is. All of these terms, this is the definition part of it now. Thanks. I'll see you in the next session, and let's move it forward.